See, the loss of vibrating string. Loss of vibrating string. The loss of vibrating string. So, when it is vibrating in one loop or two loops, suppose one loop, the frequency of vibrating string n is equal to 1 by 2L into root of T by M. This is the frequency of vibrating string. Now, if tension and linear density remains constant, the frequency is inversely proportional to length of the string. If tension and linear density remains constant, the frequency is inversely proportional to length. That is when T and M are constants. Okay. Or you can write N1 L1 is equal to N2 L2. So, you can say some first law of the vibrating string. The second one, when length of the string and linear density remains constant, the length of the string and the wire remains constant, the frequency is directly proportional to square root of tension. The frequency of the vibrating string is directly proportional to square root of tension. That is, tension is increased by 4 times, frequency is increased by 2 times, provided L and M are constants. Okay. Frequency is directly proportional to square root of tension when L and M are constants. In third case, by keeping same length, same tension, but different material, for different material where density will change or linear density will change, then frequency of vibrating string is directly proportional to square root of linear density, directly proportional to 1 by square root of linear density, or inversely proportional to square root of linear density, provided tension and length are constants. Okay. These are the basic laws of vibrating string. Okay. So, frequency depends on 3 parameters like length, tension, linear density, and we have 3 laws. This one. Then how do you prove it? Okay. So, these laws can be proved by a simple apparatus called sonometer. So, actually in physics, it is not only a theory is important, but we have to prove that theory is correct or wrong. So, this laws can be proved by a simple apparatus called sonometer. So, what is a sonometer? So, as you know, sono means sound, okay. Meter is something which measures. So, sonometer is a device to verify what the theory of this laws of vibrating string is correct or wrong. What is sonometer consist of? The sonometer consists of a string which is passing over a pulley, frictionless pulley, and the other end some mass is attached. Okay. The sonometer consists of a stretched wire, to other end of the wire mass is connected. The role of this mass is it provides tension to the string. This weight provides tension to the string. By varying this weight, I can vary the tension. By varying this weight attached to the other end of the string, I can vary the tension. Then put two knife edges. Knife edges. You can call as B1, where I can move this position of B2. For example, if B1 is fixed, I can move forward or backward. Okay. So that the length of the vibrating part I can vary. Length of the vibrating part I can vary by varying the position of B2. So, this will vary the tension, the position of B2 will vary the length. By varying the string, we can vary the linear density of the wire. Okay, fine. This setup is placed on a sound box, a wooden sound box. Okay. Now, how to vibrate the string? By using a tuning fork of known frequency. By using a tuning fork of known frequency, I can vibrate the string. Okay. So, excite the tuning fork and place it on the box on which this setup is placed. Then, due to this tuning fork vibration, it also starts vibrating. Then the vibrations of this string are called forced vibrations. The vibrations of tuning fork are natural vibrations. Okay. Now, when the frequency of the tuning fork, the frequency of this vibrating string is same, then the string vibrates with maximum amplitude. That phenomena is called resonance. Okay. What is the resonance? When the frequency of periodic force which is applied is equal to natural frequency of the string, then the string vibrates with maximum amplitude. This phenomena is called resonance. Now, so due to this, the vibrations of tuning fork, it starts vibrating, the string starts vibrating. Now, by varying B2, I can vary the L. At a particular length, both the frequencies are same. How do you find the resonance? Take a small piece of paper, bent like a shape like this, triangular shape. Keep it at center. Okay. Keep it at center, because at center the position of antinode and maximum amplitude will take place at the position center. When vary the B2 and observe the resonance. When both the frequencies are same, the paper rider which is placed at the center will fall down when both are vibrating in resonance, and maximum energy transfer takes place between periodic force and the vibrating body. It falls. When the paper rider falls, note down the length. This length is called resonating length. The very, very important thing is resonating length. Resonating length. Okay. So, in this experiment, the main thing is we are going to measure resonating length. So, resonating length is the length of the vibrating wire at which both the frequencies are same. Okay. So, what is our aim? To verify the laws of vibrating string. That is, I want to prove this statement. Okay. Frequency is directly proportional directly proportional to 1 by L or inversely proportional to length of the string provided tension and linear density is constant. Now, if I keep this weight constant, the tension remains constant throughout the experiment. Same wire linear density remains constant, like n is equal to 1 by 2L into root of T by M. I am keeping T and M constants. Now, vary the tuning fork frequency. Okay, you can use N1, N2, N3 for 3 different frequencies. Calculate the corresponding or measure the corresponding resonating lengths, and from that N1, L1, N2, L2, N3, L3. L1 is resonating length corresponding to a tuning fork of frequency N1. L2 is the resonating length corresponding to a tuning fork of frequency N2. Similarly, L3 is for N3. From this, we can prove that N1 L1 is equal to N2 L2 is equal to N3 L3. Okay. N1 L1 is equal to N2 L3. N2 L2 is equal to N3 L3. So, that is the, we can prove the first law of vibrating string. Okay. That is, the product of frequency and length remains constant. Okay. So, by varying the frequency, we can measure the resonating lengths. We can prove that product of N and L is constant when tension and linear density is constant. That is the first part. The second part is I want to study the variation of frequency with tension. How do you vary the tension? By varying the weight. Okay. You can add 1 kg weight, 2 kg weight, 3 kg weight, like this. I can vary the tension. Now, what I am doing here is, I am keeping n constant. Same tuning fork I am using throughout my experiment. Now, again same wire I use, that is linear density remains constant. I will study the relation between T and L. Okay. Let us say T is equal to mg. Let T1 is the tension in the string, that is M1g. T1 is M1g. Okay. So, and again do the same experiment. Vibrate the tuning fork, vary the position of B2 at particular length. The rider which is placed at center will fall down. Note down the resonating length. Corresponding to T1, let L1 is resonating length. Corresponding to this T1, the L1 is the resonating length. Vary the weight, which is equal to M2G, okay, and repeat the experiment and find out the corresponding resonating length. Same thing repeat for third weight, M3G and L2. So, L3 is the resonating length corresponding to tension T3. From this table, we can prove that root of T1 by L1 is same as root of T2 by L2, which is same as root of T3 by L3. Sorry. This is root is for only tension. Okay. root of t by L remains constant. So, that is what we have proved the second law. And what about the third one?